My name is K.V. Raswamy, Senior Lecturer, Electrical Electronic Engineering, Government Polytechnic, Nirmal. Today topic: Capacitor start single phase induction motor. Semester, 5th semester. Subject AC motors. Subject code 18E502 C. Time duration 50 minutes. Teaching aids, animations, PPTs and diagrams. In the last class, we have discussed working principle of single phase shaded pole motor. Single phase shaded pole motor. First, we will recap single phase shaded pole motor. After that, we will discuss in detail working principle of capacitor start motor. We already discussed about in detail what is the working principle of shaded pole motor. I will give only a line, a simple brief view. That is, a shaded pole motor simply a split phase motor. A split phase, it comes under split phase type. Generally, we know that single phase motors are not self-starting motors. It required some starting methods. Once motor starts and pick up speeds, then there is no need of starters, or we can simply, by using a centrifugal switch, we can disconnect, right? For making single phase induction motor self-starting, we will use split phase type. Split phase means simply by splitting the given single phase winding into two phase winding. That is, one is the main winding, another one is the auxiliary winding. That is the basic concept in split phase. In this case, in shaded pole motor also, pole is 1/3 of the pole is slotted, generally laminated. It consists of two parts, stator and rotor. Stator is a salient type. At a pole edge, 1/3 of the pole edge, a slot is made. In that slot, we will place a copper ring. We will place a copper ring, a closed coil. A coil or copper ring is placed. That means that portion is called shaded portion, and remaining portion is called unshaded portion. Shaded portion and unshaded portion, right? For second pole, suppose we take two pole machine. For second pole, we will reverse. So if it is a shaded pole portion, under that we will have unshaded. If it is an unshaded portion, shaded portion, opposite direction. In cross we will make north pole and south pole shaded and unshaded, right? So after making a coil or ring connected to this, just consider a simple sinusoidal alternating current, changing from 0 to maximum to 0. Let us consider three portions of region from 0 to some maximum value. At maximum, at small instant, from portion A to B, flux remains constant, and from B to C, and flux decrease. There are three types of fluxes: 0 to A maximum, at a maximum position, flux constant, at a fraction of second, flux constant, as some portion of the curve, flux constant, and remaining portion again flux decreases. The three categories: flux increases, flux constant, and flux decreases. Right? Let us consider three cases. In the first A case, current is increases, flux increases. When flux increases, what happens? In shaded portion, the EMF induces in the shaded portion of copper ring or copper coil, right? EMF is induced. That induced EMF flows in such a direction that it opposes the cause. Here the cause is increase of flux. Because of increase of flux, EMF is induced. So it tries to decrease the flux. So very simple thing is flux decreases in shaded portion and remains constant in unshaded portion, right? Very simple thing. So there is a flux in the shaded portion. Unshaded portion, flux maximum. There is no uniform flux. In a shaded portion, flux decreases. Then after that, what happens? So the most of the flux is concentrated in unshaded part, right? Why? Because in a shaded portion, flux decreases. After that, from B to C, from A to B, so flux remains constant. From portion of the curve, flux constant. When flux constant, induced EMF is 0. When induced EMF is 0, total flux remains constant in shaded and unshaded portion, right? So in that case, flux is concentrated at the center of the pole. In the first case, flux concentrated at shaded portion, right? After that, it moves to center of the pole face. Let us consider last portion, that is B to C. So flux decreases. In a sine wave, flux increases, flux decreases. When flux increases from B to C, at that instant what happens? According to Lenz's law, the cause of production of it opposes. So the cause is decrease of flux. Because of decreasing of flux, EMF is induced. So the coil circulates the current in such a way that it increases the flux, opposite. So here flux is decreasing, so it increases the flux, right? In third case, what happens? Flux increases in shaded portion. Initially, flux is concentrated in unshaded portion, next center of the pole, after that shaded portion. So flux is shifting or moving from unshaded portion to shaded portion. So flux is moving. That is rotating magnetic field. But a small, very weak magnetic field, but it is moving, right? We know that in a three-phase induction motor, if you give a three-phase supply, we get a rotating magnetic field. That rotating magnetic field induces EMF in the rotor and produces the torque and rotates in the same direction of magnetic field. In the same case, in a shaded pole motor also, if the flux is moving from unshaded portion to shaded portion, then the rotor also tries to move from unshaded portion to shaded portion. Once rotor starts rotating according to double field revolving theory, suppose if it is there are two types of fluxes in a double field revolving theory. So one is forward flux, another one is a backward flux. Suppose in the direction of forward flux, if the flux moving from shaded to unshaded to shaded portion, then the rotor also tries to rotate in the same direction continuously. Once if it starts moving, then automatically rotor rotates continuously and picks up the speed, right? So this is the basic concept in shaded pole portion of the single phase induction motor. Shaded pole single phase induction motor. Today we will discuss one more type of induction motor, that is capacitor start induction motor. Capacitor start induction motor. So we know that there are 5 types of induction motors are there. One is a split phase, already we discussed, and the capacitor start motor, capacitor start and capacitor run motor, and the fourth one is two value capacitor motor, and fifth one is the shaded pole motor, right? So we discussed through two things. One is a split phase motor, another one is shaded pole motor, right? Today we will discuss first and last one is completed, and today we will discuss second one, a capacitor start motor. Capacitor start motor. In a capacitor start motor, in this motor, the capacitor is connected in series with the starting winding, which takes leading current. As the capacitor is used only at start, it is rated for intermittent duty, and the cost of which is decreases. And the relatively small AC electrolytic capacitor is used. This motor has high starting torque and about 1.5 times the full load torque. So we can observe that diagram, capacitor start motor. So main winding and starting winding. So main winding is connected to the AC supply, and starting winding is connected in series with electrolytic capacitor and a centrifugal switch. So when the motor picks up to 80% of speed, then automatically centrifugal switch opens. Then the starting winding is disconnected. So once the motor started, there is no need of starting winding, right? Only at starting we required starting winding and a capacitor, right? Suppose if you want minimum torque, we require very small torque, then we can use only simply split phase resistive type. Suppose you want high starting torque, so we want electrolytic capacitor type of starter. capacitor start motor. In capacitor start motor, in a split phase, one winding is generally inductive in nature, main winding, and starting winding is resistive in nature. So we get a small phase shift of 20 to 30 degrees by using a resistive split phase. Split phase, a resistive type. Here split phase or capacitive type. So because of capacitance, we get more phase difference. Here in a split phase motors requires two important things. One is the two windings must be 90 degrees apart, spatially 90 degrees, spatially, right? Suppose one at the top, after 90 degrees you have to place another winding. Like the two windings are spatially separated by 90 degrees, and electrically the current passing through the two windings must be 90 degrees, in between 0 to 90. If you use one winding is inductive main winding, another winding which is placed after 90 degrees spatially, that winding must be a resistive one or an inductive one. Resistive one or a capacitor. Only two choice. Three elements are the resistor, inductor, capacitor. One winding is always constant, main winding is inductive in nature. Remaining two options are resistive, capacitive. Resistive type or capacitive. Resistive type already we discussed. Right. Then we get very small torque, small starting torque. Why? Because we get a phase difference of 30 degrees, right? Spatially and with respect to time also. We must get with respect to time, the two currents must have a phase difference 90 degrees less than. Because if you use a pure capacitor, then we get a 90 degrees. But in series with another winding we are using, starting winding, so we won't get exactly 90 degrees phase shift, right? So there is some phase difference between two currents of main winding and starting winding, right? In a split phase motor, a high auxiliary winding circuit resistance creates a phase angle between the currents of the main and auxiliary winding. This phase difference between IS and IM, starting and main winding, can be produced by connecting a capacitor in series with the auxiliary winding, right? In a capacitor start motor, an electrolytic capacitor along with a centrifugal switch or relay is connected in series with the auxiliary winding, which is shown in figure 3.8. The capacitor is usually mounted on the outside of the motor as a separate unit. Right? Here assume the current in the main winding is IM, the current in the starting winding is IS. We have to provide some phase difference between IM and S. That is the basic concept, right? We have to provide some phase difference between IS and IM. In case of a three-phase induction motor, if you have three currents, IR, IY and IB, automatically we are giving a three-phase supply. There is a phase shift of 120 degrees between each and every current. So automatically we are getting a rotating magnetic field. Here we have to create some phase difference, right, in between IM and IS. Right? IM is always an inductive nature, lagged by some current. IM current lags voltage with some angle, not exactly 90 degrees, less than 90 degrees. And similarly, current passing through the starting winding, we have to make current passing through the starting winding is a resistive type or a capacitive type. So we are using capacitive type. So we will connect a capacitor in series with starting winding, and a centrifugal switch also connected. to the starting winding. Right? In a capacitor start motor, an electrolytic capacitor along with a centrifugal switch is connected in series with the auxiliary winding. The capacitor usually mounted on this outside of the motor as a separate unit. It is mounted on the motor as a separate unit. When the motor is switched on, so observe the phasor circuit diagram. So here Im represents the current passing through the main winding, Is represent current passing through the auxiliary winding or starting winding. We are giving a single phase supply. And the rotor is type A, it is squirrel gauge type. Squirrel gauge type means copper bars or aluminum bars are short circuited with the two end rings. Then it just looks like a cage, squirrel cage. Right? So these small circles represents conductors. They are short circuited by end ring, round end ring, and a dashed circle, hatched circle represents in the diagram. In the diagram, it is a shaft. Here S is a switch, and C is a centrifugal switch. C is a capacitor. S is a centrifugal switch, and auxiliary winding, that is a main winding. Current passing through is Is. Right? Observe the phasor diagram. Here V is the applied voltage, which is along x-axis. Right? And current Im is lags. V and Im is lagging. Observe here, V and Im is lagging. Right? So when the motor is switched on, to the supply means current Im drawn by the main winding lags the supply voltage V by a large angle, where Is drawn by the auxiliary winding leads V by a certain angle. Right? When the motor is switched on to the supply means current Im drawn by the main winding. The current Im drawn by the main winding lags the supply voltage V by a large angle. Why? Because it is inductive in nature, so it lags some large angle. Whereas Is drawn by the auxiliary winding leads V by a certain angle. One is a lagging, another one is a leading. Im lags with supply voltage V. Is leads with a supply voltage V. But very small angle, leading by a very small. Why? Because already it is connected in a series with some winding. It is already in some lagging in nature. We are applying a pure capacitor. So overall leading angle is decreases. Right? The two currents Im and Is are out of phase. With each other by nearly 80 degrees to 90 degrees as compared to nearly 30 degrees for split phase motor. Right? The two currents Im and Is are out of phase with each other by nearly 80 to 90 degrees as compared to nearly 30 degrees of the split phase motor. Clear? Very simple thing is, in a split phase motor, generally in a split phase motor resistive type, high auxiliary winding circuit of resistance, its resistance creates phase angle between the currents and the currents of the main and auxiliary winding. This phase difference between Is and Im can be produced by connecting a capacitor in series with the auxiliary winding. Just by connecting capacitor, we will get a phase shift. Right? In a capacitor start motor, generally we use electrolytic capacitor, not paper capacitor, electrolytic capacitor. Why? Because by using electrolytic capacitor, life is more life. We can on and off, charge and discharge continuously more times. That's why we use electrolytic capacitor. And for only starting, and that means electrolytic capacitor for small duration, but number of times we can on and charging and discharge, but a small duration. Time constant is very less. Along with the centrifugal switch is connected in series with the auxiliary winding, so this is shown in figure, and the capacitor is usually mounted on the outside of the motor as a separate unit. So observe the phasor diagram, right? V, Im and Is. Im lags, Is leads. The resultant will be I. So which is some again lagging with some voltage. We again lagging one, that is again in inductive in nature, right? So when the motor is switched on, the supply mains current Im drawn by the main winding lags the supply voltage V by a large angle, whereas Is drawn by the auxiliary winding leads V by a certain angle. Im lags by a large angle, but Is leads by a small angle. Why? Because we cannot provide a pure capacitor, right? A capacitor in series with a winding. That's why we get a small leading angle. Then the two currents Im and Is are out of phase with each other. By nearly 80 to 90 degrees as compared to nearly 30 degrees of the split phase motor. So the resultant current Is is small and is almost in phase with V, as shown in figure second B. In the figure B we can observe that almost in phase with V, and causes the motor to start once the motor has pickup speed. Once the motor has pickup speed, the centrifugal switch or relay operates and opens the auxiliary winding circuit. The centrifugal switch or relay operates and opens the auxiliary winding circuit. Right? So, in case of a split phase motor, angle between Im and Is is only nearly 30 degrees, but in this case, here we get phase difference of 80 degrees between Im and Is, 80 to 90 degrees, right? So we get almost a continuous rotating magnetic field without any jerks, right? A smooth operation also we can get at starting. Then we will get a high starting torque. Next, the starting torque of a capacitor start motor is of the range of 3 to 4 times the full load torque. The main advantage of capacitor start motor is of the range of 3 to 4 times its full load torque, whereas for a split phase motor it is only 1.5 times only. So typical torque speed curve of a capacitor start motor is shown in figure. Torque speed curve characteristics. Torque speed curve of a capacitor start motor is shown in figure. You observe the diagram, right? So in that case, on x-axis we will consider 0 to 100, that is percentage of the speed, and torque from 0 to 400, the percentage of the full load torque. Generally, torque is zero and speed is equal to 0. If a dashed line, if you observe the dashed line, so at 0, when speed is equal to 0, torque is 0, right? So generally observe, right, 100, percentage of speed is 100 when it's continuously rotating, right? So slowly at starting there is no starting torque at all for normal motor, so the starting motor is 0. So once if you rotate by any means, then slowly speed pickups and motor also torque also pickups and moves to maximum. So after getting 75% of speed, after that again it decreases. When speed goes to synchronous speed, then automatically we know that again torque becomes 0. It goes to synchronous speed, equal to synchronous speed, again torque becomes 0, right? Generally here we get 3 to 4 times. If you observe the torque diagram, 0 in between 300 to 400%, 3 to 4 times, 3 to 4 times of full load torque, 3 to 5 times of full load torque, right? So that is a main and auxiliary winding. By using main and auxiliary winding, right, without any auxiliary winding, just if you rotate by means of your hand, then this is the dashed line represents without starting methods. So torque is 0 and motor speed is equal to 0. Once if you rotate with your hand, then rotor rotates, slowly pick up the speed, then that is the second dashed line curve, torque speed curve. So actually if you use a capacitor start motor, right, where is a high starting torque, you have to 0 to 3 to 4 times, actually 0 for without any starting method, right, and 1.5 times for split phase motor, 1.5 times for split phase motor, right. This is 3 to 4 times for capacitor start motor, right. So we can clearly understand that the starting torque is very high, and after that when speed picks up speed and the torque slowly decreases, right. When it goes to synchronous speed, automatically you know that when equal to synchronous speeds, torque becomes 0. So this is the torque step characteristics of capacitor start motor. Very clear, right? So simply by giving the supply when the motor is switched on the supply means current IM drawn by the main winding lags the supply voltage V by a large angle, whereas IS drawn by the auxiliary winding leads V by a certain angle, right? And after that the two currents IM and IS are out of phase with each other by nearly 80 to 90 degrees as compared to nearly 30 degrees for a split phase motor. This resultant current I is a small and is almost in phase with the V as shown in figure, and cause the motor to start. Once the motor has pickup speed, the centrifugal switch or relay operates and opens the auxiliary winding circuit. Then the starting torque of a capacitor start motor is of the range of 3 to 4 times the full load torque, whereas of the split phase motor it is 1.5 times only. So the typical torque strip curve you can observe for capacitor start motor in figure 3.9. So it's a very high starting torque, right? So once again we will go for working principle of capacitor. Just we observe phasor diagram and starting torque and torque slip characteristics, right? Here working of a capacitor, how a capacitor will work. The capacitor here the capacitor used is a dry type electrolytic one, designed for AC use only, dry type electrolyte. It is different from a DC electrolyte type capacitor used as a filter in radiators, amplifiers and television. So we know that a capacitor is also used in televisions, radios as a filter circuit. That is different from this one. So the starting capacitors used are designed for extremely short duty service, very short duty service, very small variation, but very large value for a small variation, small time. Short duty service, not for continuous operation, only for a small duration capacitor will work. So it is guaranteed for less than 20 periods of operations per hour, okay, in an hour. So it is operated only for 20 periods of operation per hour, each period not to exceed 3 seconds, okay. So whatever the electrolyte we are using, it must be operate only in 3 seconds. Within 3 seconds we have to the motor pick up the speed and the switch must be open. And in an hour only we must use only 20 times. Don't switch on and off continuously a motor. Right? And it is because of the development of the inexpensive AC electrolytic type capacitor that capacitor start motors have become very popular and found wide applications where high starting torque is required. Right? A faulty switch may keep the auxiliary winding together with a capacitor engaged for a long time and thereby shorten their lifespan. Right? So this is electrolytic capacitor, working of electrolytic capacitor. Right? So once again I will explain what is the working principle, main working principle of capacitor start motor. Just a small brief view. Already we discussed in detail. We have some time to discuss. So I will explain once again. You can understand very easily. Right? Very simple basic thing I will tell. First one, it is a split type. It is a split phase type. That means one winding is divided into two windings. So one is a main winding and the other one is auxiliary winding. Right? So we already discussed one, that is split phase resistive type. In case of a split phase resistive type, flux variation is very small. Or the phase angle between IM and IS. So we will consider that IS is the starting current and IM is the current in the main winding. IM is the current in the main winding. IS is the current in the starting winding. Right? So angle between IS and IM is very small, nearly 20 to 30 degrees only. So this is the basic idea. If this angle is very large, then we get a smooth rotation. We'll get a smooth rotating magnetic field. So we can provide a smooth rotating magnetic field if we provide a large phase angle between IM and IS. IM and it's main winding and starting winding current. Main winding current and starting winding current. But in case of a resistive type, we will get only 20 to 30 degrees of phase shift. Right? First, the two windings must be 90 degrees. Spatially, they are 90 degrees phase difference. Right? And with respect to time also, we have to provide a 90 degrees phase shift. But because of a resistive type, we get only 30 degrees, 20 to 30 degrees. So to improve, because of that, we get a very small starting torque, only 1.5 times of the full load torque we will get at starting by using a resistive type. So to improve the starting torque, we will consider capacitor type. We will use the capacitor type. Right? So in case of a capacitor type, we will connect a capacitor in series with the auxiliary winding with a centrifugal switch. In series with the centrifugal switch. Right? So because of connecting a capacitor, the IS becomes lead by some angle, a small angle with a voltage V. Right? In the first case, again it is lagging only. Right? In a resistive type, it's simply lag, a small angle with a voltage, lagging angle. In a capacitor type, leading current with a small angle but a leading current. Right? So a capacitor is connected in series with a centrifugal switch. Right? Next, so when we apply supply, when supply to the single phase induction motor, what happens? When supply is given, voltage, current divides, total current I divides, observe in the diagram, I divides as IS and IM. IS is the current in the starting winding, IM is the current in the main winding. Okay, main winding is inductive in nature, so it lacks very large angle with a voltage V. Where IS is the current passing to the capacitor. Capacitor means it must provide a leading current, So, suppose if it is a pure capacitor, then we get a 90 degrees leading, but there is an auxiliary winding here in between. So because of that, we'll get only a small phase angle, leading phase angle with a capacitor C, right? You can observe in the phasor diagram also. V, IM and IS, a small leading angle, here large lagging angle. So because of that, we will provide very high large angle between IS and IM, which is responsible for for getting a rotating magnetic field. So it is 80 to 90 degrees phase shift we can provide in a capacitor start motor, right? So so IS drawn by the auxiliary winding leads V by a certain angle. Then what happens? Then the two currents IM and IS are out of phase with each other by nearly 80 to 90 degrees as compared to nearly 30 degrees of split series motor. The resultant current I is small and is almost in phase with voltage, and cause the motor to start. Right? To start the motor, we require rotating magnetic field. How a rotating magnetic field provided? Simply by providing a phase shift between the two currents. How we are provided two currents? Simply by using a split phase. Phase is divided into two windings, main winding and auxiliary winding. Okay, we are providing a phase shift between starting winding and main winding. Then we get a rotating magnetic field. This rotating magnetic field rotates the rotor. So once the motor rotates, then what happens? Once motor rotates, then it picks up the speed. The centrifugal switch or relay operates and opens the auxiliary winding circuit, simply opens. Right? Why? Because the electrolytic capacitor is designed only for a short duration, nearly less than 3 seconds. Within the 3 seconds you have to disconnect, otherwise we get life of the capacitor decreases. Right? Opens the auxiliary winding circuit. So this is the working principle of capacitor type of 3 single phase induction motor. So observe the torque slip characteristics. So here a dashed line, you can observe the dashed line, the torque slip characteristics. Zero torque for zero speed. When speed increases, torque increases and goes to maximum, comes to zero. Right? Without any starting method, this is the procedure. Without any starting method, simply if you rotate with your hand, then this is the torque slip characteristic. Suppose by means of capacitor, if you rotate it, if you start the motor, then we get, you observe from 300 to 400, in between 300 to 400, 3 to 4 times of full load torque. 3 to 4 times of full load torque we can get at starting. At starting we'll get 3 to 4 times of full load torque. Starting current is very high. So that is the main advantage. The starting current of 3-phase induction capacitor motor is very high. For split foot motor is only 1.5 times only. Right? And one more important thing is the working of a capacitor. The capacitor used is a dry type electrolytic one, designed for AC use only. It is different from DC electrolyte capacitor used as a filter in radiators, amplifiers and television, etc. The starting capacitor used are designed for extremely short duty service and not for continuous operation. Right? So it is guaranteed for less than 20 periods of operations per hour for each period, not to exceed 3 seconds. So it is because of this development of inexpensive AC electrolytic capacitors that the capacitor start motors have become very popular and found very wide applications where the high starting torque is requirement. So a faulty switch may keep the auxiliary winding together with the capacitor engaged for a long time and thereby shorten their lifespan. right? This is the working of a capacitor, right? You have to remember only two important things. In a capacitor start motor, we can get high starting torque, 3 to 4 times the full load torque, right? And another important point is we can provide a phase angle of 80 to 90 degrees between starting winding and main winding, main winding, right? These are two important things. And again, it is a electrolyte capacitor, AC use only, and designed for only for short duration, less than 3 seconds, and you can operate only 20 times per 1 hour. In 1 hour you can operate only for 20 times, otherwise life of the capacitor decreases, right? Thank you very much.